Hello and welcome back to another tutorial video in redox chemistry. This video will be dedicated towards the rules of oxidation numbers. So first we'll just be covering what they are briefly, and then we'll go into the rules and explanations. So the definition of an oxidation number is that an oxidation number or an oxidation state of an atom represents the number of electrons it theoretically transfers to become part of a chemical compound. These numbers can either be positive, negative, or zero. But there are 5 rules to abide by. But before I go on to the 5 rules, I just want to go over some convention. So typically we have, in chemistry, we denote the charge by the number and then plus or minus. But in oxidation numbers or oxidation states, we denote oxidation number by plus or minus and then the number. Now this is just convention, but we'll when we get to rule 5, then you can finally get a grasp of why they're important. Okay? So the first rule, the oxidation number of a monoatomic ion is proportional to its charge. So a couple of examples would be that, let's just say that we have titanium 4+. Its oxidation number, which I'm just going to denote as O.N, this is going to equal +4. We also have another example. Let's have chlorine minus. Its oxidation number is going to equal -1. And then let's have one final example. Let's have calcium 2+, and its oxidation number is going to equal +2. The second rule of oxidation numbers is that an oxidation of a free element, or another way of saying a free element is a compound containing only one element, that oxidation number is 0. So a couple of examples of this. Let's just take an example of a free element and then a compound with only one element in it. So if I just draw a margin through that, let's just say that I have pure iron. Now since iron is by itself, its oxidation number is going to equal 0. Now let's take a compound or a molecule with only one element in it. Let's say that this is going to be oxygen. Now there's 2 oxygen atoms in it, so its oxidation number is going to equal 0. So the third rule of oxidation numbers is that if hydrogen is bonded to a non-metal, its oxidation number is going to be +1. On the other hand, if hydrogen is bonded to a metal, its oxidation number is going to be -1. So just a couple of examples for this slide. So if I take hydrogen bromide, and let's say that I'm going to separate them. And I'm going to separate them via electronegativity. So if you remember anything about electronegativity, the elements that are closest to fluorine are highly electronegative, so they want all the electrons. So if I have all the electrons, I'm going to have a high chance of getting a negative charge. So in this case, bromine is closer to fluorine, so I'm just going to write this compound like this. So bromine has a negative charge because it's more electronegative. So now I can just use my rule 1, where the oxidation number is proportional to the charge. So here we can see that the oxidation number of bromine is -1, and the oxidation number of hydrogen in this case is going to be +1. Now let's have another example where we have calcium hydride, and we're going to do the same process. So we're going to separate them. Calcium is going to be more electropositive in this case. It's going to be further away from fluorine. And hydrogen is now going to be more electronegative. I made a bit of a mistake there. So in this case, hydrogen, or in this case the hydride anion, its oxidation number is going to equal -1. So rule 4 says that the oxidation number of oxygen in any compound is -2. The only exception to this is in a peroxide, where oxygen is now -1. So if I have just 2 examples and do one for any compound that isn't a peroxide, let's just have water. And I'm going to use my separation process for electronegativity and separate them into O2 negative plus 2 lots of hydrogen positive. So here we can see just via rule 1 that oxygen now has an oxidation number of -2. Now if I have a peroxide example, H2O2, and I use the exact same process of separation. If I have 2 lots of O2 negative plus 2 lots of hydrogen positive, there's something about this line that doesn't make sense. So here, if I add up all the charges, I'll get 2 lots of 2 negative, which is going to be -4, plus 2 lots of +1, which is going to be +2. So if I add them together, -4 plus 2, that's going to give us an overall charge of 2 negative. But it's not 2 negative to begin with, so there must be something wrong here. So if I change the charge on the oxygen to 1, this will make sense. And that's indeed what happens. But next rule, it will all make sense. Of oxidation numbers is rule 5, and that says that in a polyatomic compound, the sum of all oxidation numbers must equal the overall charge of the compound. So if I just prove the hydrogen peroxide one again, just using a different rule, I just write it like this. Using rule 5, I can set this out by just writing 2 oxygen, and I'm just going to say OX here because my O's look like a whole lot of zeros to me, plus 2 lots of hydrogen. This is going to equal the overall charge of 0, since hydrogen peroxide is neutral. So using rule 3, hydrogen is bonded to a non-metal. So 2 lots of oxygen is going to equal 2 lots of positive 1, which is equal to 0. So 2 lots of oxygen is going to equal negative 2, and then we divide both sides by 2. So oxygen is equal to negative 1. And that's what answer we got from last slide. So if I have another example, H2PO4 negative. So using rule 5, I can use that 2 lots of hydrogen plus phosphorus plus 4 lots of oxygen is equal to negative 1. So using rule 3, that hydrogen is bonded to a non-metal, its oxidation number must be positive 1. And using rule 4, in any non-peroxide compound, oxygen is equal to negative 2, I can just write this out now. So 2 lots of positive 1 plus phosphorus plus 4 lots of negative 2 is equal to negative 1. So we would get now that P minus 6 is equal to negative 1, and thus the oxidation number of phosphorus is equal to positive 5. So hopefully that all makes sense, and yeah, I'll see you in the next video.